So, good morning, everyone. I'm very happy that we can be here. It is, after COVID, is year one of conferences. So, what I am presenting here is joint work with Hugo Parlier. I hope that it is big enough that you can read it from the rear. Can we perhaps turn off the lights? So then I will also say hello to the persons who are behind this camera. So my original plan was to present final work on these algorithms, and I worked very hard the last few days, as my wife can tell you, and so this is rather work in progress, and we do not have final results, but as a work it is quite thrilling. So, I want to dive into the subject, and then I saw that there's some other talks that are maybe a little bit connected. So, I saw that on your abstract there is Heinz Huber.
There's one?
Huber.
Yeah.
So, you have Huber's theorem, and Huber was my thesis advisor. And so I thought maybe I should say a word not about his life. He was kind of a shy person. You didn't see him on meetings, but he was actually the person who created the term of length spectrum. So in his thesis already in 1953, he used the term moduli spectrum. So somehow the moduli of ring domains came in. And then later he called it the length spectrum, and he discovered the asymptotic law that if you look at the closed geodesic on the Riemann surface and you count them, counting is very interesting, and I think we would talk about this the afternoon, so I thought this may be a connection. So if you count how many geodesics you find between length 0 and L, then there is exponentially many, more precisely e to the L over L, that's the asymptotic number that you get. We will not talk about this, I will not talk about this here, but I wanted to mention it. And if my time is not running out at the end, I will come back to this. So, about geodesics, there is of course a tremendous literature. I just will give you some stages. So in 1984, I already had students at 1984. The permanent series were not students. They had an algorithm for simple curves. There are many algorithms. How to detect how many intersections you have, and so on. And I mentioned them because they also, probably while working on this, they discovered that the simple curves are sparse. So the closed geodesics are dense on the Riemann surface, but if you look at the simple ones, they're actually nowhere dense, and that's a result. I will not talk about this either, but this is in a way the background of the story. Then I would also like to mention Neil Sakani, 2009, who attacked the question whether it's possible to get an asymptotic law for the simple geodesics. And that's a completely different matter. And I must say that I do not understand the first law, nor do I understand the second law. I can give a proof, and after having given the proof, I still have a feeling, okay, it's true, but I do not see it. So this is actually a little bit mysterious, And then Berman and series have this set of closed simple geodesics. And then some time ago, I was interested, and Hugo also, in representing the curves. What you see here in the picture is a fundamental domain, which is two surface, Riemann surface. And here I have drawn by some early algorithm, which is not so really precise, a bunch of several hundreds of thousands surfaces. If you close up, you see something like that. But the question is that what you see? And that's also work in progress with Hugo, that when the computer produces a picture, it's okay, it's a picture, you can look at it, but the question is that what you get? So this is what we would like to do. Oh, my phone is also. So let's hope. Anyway. So Gabino, you have seen this picture on some sunny day in Madrid in 2009. We need an enumeration algorithm. This picture will show up in a second. And so the thing is, we have to represent, or Hugo and I would like to represent the closed geodesics, but first you have to get them together. And if you enumerate closed geodesics, and in Aloya in 2007, I presented an early algorithm which was very clumsy, and I presented it to these people. I think I cannot make it bigger unless I will destroy it, but you can see some persons who are actually in this room. Here is one, I guess. And this is Ara, and here is one organizer, and I apologize that I do not have the second organizer. So, algorithm for simple curves on 3 regular ribbon graphs. That is actually the talk I will give now, because if I do the introduction that long, I will never come to the subject. The idea was to take this early algorithm and make it a little bit more systematic. And the first thing that we are actually trying to do right now is to do a completely combinatorial algorithm. So the world of hyperbolic geometry is getting into the background. I show you a picture of something that is already working in the algorithm. I don't know whether I want to explain what you see, but I try. So, the thing is about graphs. This is a graph. And then what's a ribbon graph? A ribbon graph is the same graph, but you make it a little bit thick. So instead of thinking of lines that you draw, you think of like paper strips. The combinatorics of a ribbon graph is the same, but the idea for the ribbon graph is that you see a little bit better if you do drawings on it. So lately, such ribbon graphs are quite, you can see them a lot in the literature. 3 regular means that at every vertex you have 3 points, and then the 3 regular ribbon graph is the same thing. On ribbon graphs you can draw edge paths. Oh. There. So you go along the paper. And simple means that there are no self-intersections. Here you have a counterexample of a path that would self-intersect. And here is an exercise. Don't be nervous, it's not very difficult. exercise is find all the simple closed edge paths on the following example. Here is the example. Here are the vertices. This is part. So this is paper, and this is a hole, and this is also the blackboard. So, how many closed paths, simple ones, can you draw there? Okay, coffee break. The thing is that when you try to solve this problem, it's very difficult, then you get right into the idea of how an algorithm might work. Hyperbolic geometry is far in the background. So, what do you do? What you maybe not see is that I have vertices here just to mark the idea that this triangle is not a road sign, but it's a written graph. And the first thing you try to do, you start somewhere. I should say up to choice of beginning and orientation. You do not look at oriented curves. And there is also something before you start. Going forth and back on the same movement. Like you go forth and then back again, something like this. This is not a line, this is considered a self-intersection. However, if you go around a path and you come along the same edge when you return, because it's a written graph, you can move a little bit away and then you get a simple graph. So this is not considered a self-intersection. And in meanwhile, you have solved the problem. So let's see. We will, excuse me, so I solve it. You start out at an edge. And come on, voila, beautiful. And then you come to a question. Because now you have to continue. There is only one edge. Returning is not allowed. So the only thing you can do is go into this edge. And then the same problem shows up again. And okay, you return and you have your first closed path. The algorithm now says, okay, that was one. Is there anything else I can do? Of course, I can try to continue. You see here, I go to the right, but now you see that when you enter, you will never be able to close this again, and so the final solution is that there is only one. So for such examples, the problem is very easy. But you have seen the flavor of an algorithmic idea. Now let's see another one. I have some hand drawings. So I don't know whether this symbol has anything. So it should just be a written graph, hand drawn. And now you have the same question again. So maybe I take another picture in the future, but that's the one I have right now. So, and this already needs an algorithm. Already a first step, a little bit more complicated, and this is the written graph that was shown in the first picture, and then for the presentation of the algorithm, how the algorithm works, because we do have a little part of an algorithm that is implemented, so there is code for this, and if you look at the figure, from now on you should imagine that the vertices 1, 2, 3, 4 are represented by these hexagons, and the arms are here. And from now on, let's make this a little bit bigger. And here comes an algorithm. You start at some point, draw the first line, have a look at the time which is left, and then you go in one direction. And now you have to imagine that you are a little animal a little beetle that is creeping along this paper band, and it is supposed to draw for you all the simple closed curves, paths, say up to some length, because you do not want to exhaust the poor animal. Animal has very little memory, so it is maybe like a spider who can draw lines, spider web. So it is possible for the animal to draw lines. And what else does it do? I don't know. Every time the animal comes to a bifurcation like here, the poor thing doesn't know whether I should go to the right or to the left. That's a decision. And in algorithmic terms, making a decision is always considered something that counts for time. So an algorithm that needs a lot of decisions is considered complicated. And for the animal, it's complicated. So in order to simplify its task, you say whenever you come, if it's possible, don't mind, just go to the left. Okay? So it goes to the left. I can tell you when I do these doodles before drawing here, after a while, I don't know what is left and right. That's another thing. So this goes to the right, which means that if you're on it, then it goes to the left. So the animal goes to the left, and you can see that it is actually closing up. Up here, this is connected. I did not draw the connection, so you have to imagine this is connected to here, and so it got its first. Okay, it's drawn, and then it will just call you and say, here is one, and then you have to copy it. In the meanwhile, the animal continues creeping around. I have pushed this line a little bit apart, and so it continues here. And now it doesn't have to do any decision at all, because it's not allowed to do any crossings, that it knows. So it will just go along here. So there are some steps where there is no decision to be made. It comes up again up here. It makes what it can. And after a while, it gets exhausted. Because here, for instance, I said if you have more than 10 lines, give up. Okay, and then the animal, if it's exhausted, it goes back to the last point where it made the decision and starts all over again. And the only thing that it has to remember is, I went left. I do not go left at this place a second time. So we go right, if it's possible. And that's actually the algorithm, you see, up there. Duck, duck, it goes to the right. Because left, it did already, and then it goes on, and so on, duck, and here is some nice simple closed paths. So I remember that we were sitting at some place in Lausanne, and saw these figures, and thought it's quite thrilling, so I show you just a few of these. So this is the algorithm that works on ribbon graph that we have seen here. And I just gave some examples. They look all a little bit alike. So you can draw. This is certainly not a hand drawing. You cannot do that many. And of course, it's almost impossible to tell whether this is one simple curve or whether there are several ones. So you have to trust actually that these pictures are correct. If you want to see, you have to go along the lines. It's very complicated. That's ribbon graphs. But we are in surfaces, in Riemann surfaces, even Klein surfaces, although I do not have them. So, I want to explain to you what is a ribbon graph that's useful for a Riemann surface. First of all, for a topological surface. As always, when you see a picture, you don't know what it means. So I have to give an explanation. Here I try to draw a space figure, just in order to give an idea of a pair of pans. Suppose this is part of a surface or a Riemann surface. you draw some closed geodesics, and more of it, and then you have a pair of pans. And I shaded it a tiny bit to show that this should be some sort of a 3D figure. Okay, now I draw a particular small. Well, I should have made a bigger picture. I hope you can see it. So around the geodesic, I draw a parallel one here. So this gives me a first band, which is part of a ribbon graph. I repeat this on the other two, and so the three cuffs of the pair of pans are now wrapped in a little paper band. That's part of the ribbon graph that I'm going to design. Then you take I tend to say geodesic, but this is combinatorial. You take a curve that goes from one cuff or end on the back side, here. And I have a question for Hugo. Is this a roaming ortho?
Absolutely.
Is it? And where is it roaming? I mean, here it just goes back. That's it. Anyway, so I thought maybe this is roaming geodesic, and then you do a paper band around it. So and then you repeat the exercise a second time on the other side, and on the third. And now it's already nicely wrapped in. It's still not enough for an algorithm to be working. By the way, from the other sides, the adjacent pairs of pans, you do the same thing. But we also need the, in geometric terms, orthogeodesics between boundary components, 1, 2, 3. Same thing on the other side. And now the surface is nicely wrapped in. You can think it's Scotch tape, like if you travel and you want to make sure that nothing gets lost, you do a lot of Scotch tape. The mathematical question is, would that be enough to guarantee that you get the closed curves directly? For practical reasons, these three-dimensional figures are not so good, so we draw the same thing in the plane. Here you see part of the ribbon graph. Next, just have a look.
Just have to have you see this.
And then in the algorithm for the remember the beetle that creeps, you have to draw these lines and has all this little memory. Now you say what you do is actually necessary to give you curves on the surface and not on the ribbon graph. And so there are two things that you must follow. No bridge crossings. So you tell no bridge crossings. It doesn't know what you mean. And don't exit on the entry side. So I have to explain what I mean by that. The ribbon graph has the vertices here, but these intersections that you can see, these are not vertices of the graph. This is just the paper bands are overlapping. And if the beetle has, to go back a little bit, yes. If it has, for instance, in the first place, down here, then it has drawn a line. So when it would like to follow that arc, it's not allowed. Because on the written graph that would be fine, but for us, we want these curves to be simple on the surface, this is not allowed. So whenever there is a bridge that's already occupied by something the beetle has drawn, this is not allowed to be followed later. It's also not allowed to enter on some side, go around and then leave on the same side, because a curve like this can be homotoped away from the pair of pans at all, and then you would have a multiple representation of curves and that you want to avoid. Okay, so this is all the animal has to know. So we go back to the ribbon graph. You have to understand what it means. From left to right is closed. So this is one of the rings. And there were 3 cuffs. So you see 3 things here. And anyway, it's the same thing. So you can see the beetle actually is hasn't forgotten. You see there, oops, it goes to that side and it wants to go left because that's what it learned at the beginning. But if it would leave to the left, it would mean that it actually leaves on the same side because up is the same side. So it knows that it is not allowed and therefore it goes right. And then it continues, and when you write an algorithm and it finally works, it's very nice. So you watch tons of pictures, but for the audience it's maybe a little bit tiresome. But see, here are some curves that are on the ribbon graph, but they also can be interpreted as curves on a genus 2 surface. One more, that's it. So, what about the bridge crossings? Not allowed. If you like to watch what the algorithm does, you can also represent all the crossings. That takes enormous time to do the programming of this. Anyway, here it is, and you can see at all stages, when one bridge is occupied, the other bridge is not occupied. So the beetle has done its work correctly. Here are some. And where are the Fuchsian groups? So this algorithm is designed to do simple closed curves, and we have to prove that it gives the simple curves, all of them. And the special emphasis is made that the curves are not obtained several times. So at the end, when you have all the curves together, you do not have to bother with looking whether several ones, whether you have the same curve a second or a third time and so on. But where are the Fuchsian groups? So time is already a little bit running out. When you think of these curves that I've shown with the question to Hugo whether this is a roaming ortho-geodesic, it means that from a hyperbolic geometry point of view, these curves are orthogonal on the surface, on the boundary of a pair of hand. And so every pair of hand is decomposed into hyperbolic rectangular hexagons. And if you lift these hexagons into the hyperbolic plane, the universal cover, you get a tessellation by hexagons. And what you can see are these orthogeodesics, and that's actually where the beetle crept along, seen from a hyperbolic point of view. And therefore, you can say that the element of the Fuchsian group, that this closed curve that this animal has finally discovered, if you look at these closed curves and lift them, you can say the isometry of the Fuchsian group that corresponds to this closed curve can be represented by a product of an isometry in one direction, an isometry in the orthogonal direction, again an isometry, the orthogonal direction, and so on. So all you have to know is these lengths that you get by geometry. I haven't written up the matrices that will do this, but once you have the curve, you can translate it immediately into a product of right, for left and right, or up and downs. and there is the Fuchsian group. I should give you the formulas, but time doesn't permit. I'm coming to the end. So, by the way, what we have here is a fundamental domain of the Klein quartic, but not represent, or maybe it's a perturbation of it. So the fundamental, yeah, they should be isometric and they don't look. So probably I missed something in the choice of the example, but the big hexagons that you see from this, and this is one fundamental domain, and then you see the tessellation more of this. So once you have a closed curve on the Riemann graph, you have immediately corresponding element in the Fuchsian group. What our next step? The next steps are, we would like to draw we would like to show the Riemann series set, that is the set of all simple geodesics, complete geodesics, on one picture. Now there are uncountable many, so this is a little bit asked a lot, but we try. The thing is, when you do, when you draw a geodesic, you have to use I mean, it has to be seen, so it is thick a little bit. And so when you have many geodesics, they come so close together that it is not necessary to present them all, because they're all in such a small neighborhood of each other that you just see them as one. That's a little bit the idea. And then I asked Hugo to send me the latest version of the theorem, but I thought it's maybe good not to show it too fast. It's just a proof that we work on theorems as well, and not only. And then there is some other work to be done. Antonio, I said that we had some project on issues that have to do with calculation of matrices, which is not so precise as one thinks. So there is a project of bypassing numerical issues using geometric argument. This is also work in project, not in progress yet. And then I have a final remark about the asymptotic law. So I come back to the beginning. I think I'm already in time. So this is one of these curves in a very simple situation. It's just a graph that, what's it, four-hole sphere. So when you look, so this is Mathematica, screenshot of Mathematica. Work 18 means that Mathematica had the task here to draw all the geodesics, or the simple curves, that have 18 strands. I also was interested in the absolute timing, and current beef doesn't mean anything right now. So the number of closed curves that it detected was 19. The number of all the curves where the beetle was exhausted because it ran out of strands that it was allowed, and didn't find a closed curve that would creep back. So we counted how many times that happened. So the frustrations was 501 and the successes 19. And so we can look at the statistics: 18 strands, 19 curves fine, 501 unused, and 1 second of computation time. Here is a little bit later, 358 strands is already quite a lot. And we have 7,369 closed curves. you can't draw them anymore on the figure. 3 million and so on. Frustrations. The computation time was 31,000 seconds. So that was the program running overnight. And when you do a statistics of this, I never understand statistics, because when someone gives you a statistic, he just, here you see, and it doesn't explain what is the horizontal line, it doesn't explain what's the vertical line. And I forgot what's the horizontal line. But it looks like statistics, right? So in the meanwhile, I remember. So here is the number of strands, 20, 40, 60, 80. And then the number of closed curves that you get. And we take the number to the power of 3.7 over the number of, what was it, curves. I forgot what it was. Can you remember?
Yeah, it's the number of, you just said it, right? It's the number of the simple ones that don't close up versus the simple ones that do close up.
Yeah. So you get some nice statistics, and it's and what's important is, if you look at it, it seems to level out here at some horizontal line, and that's an asymptotic law. And maybe on these combinatorial examples, you can understand asymptotic laws a little bit better, or maybe you can understand it better in your talk here as well.
So, questions? Anybody has a question? So I have one, if I understood it correctly. So you record these choices of going left or right, and then you translated it in the function group version, like going up or...
Yeah, you have to understand, I do not have a demo of this, but you have to understand that you have the fundamental domain of this, so you lift the whole figure along the vertical, and then another right angle comes to the center, and then you move it to the right, and then another right angle comes to the center, and so on. And when the curve is run through, another fundamental domain has just been sent to the center. And so therefore you have a deck transformation. So you have to think that you have the first fundamental domain, and you shift duck, 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 and at the end you have another fundamental domain. So this product is an isometry that sends a fundamental domain to that one, and that's an element of the Fuchsian group.
So you get a word in so many elements of the group as choices of, or it's not that.
Yeah, well, these vertical and horizontal are not they're not in the Fuchsian group itself, but you write a word like that.
Yeah.
So it's an auxiliary word, and that you can also write explicitly the element of the Fuchsian group as a product of these words.
Okay.
So you started out with a fancy composition. So are you thinking of that for a particular Riemann surface? Are you thinking of that where the pants curves are all very short? So that because
that's a trauma.
Because you could choose a really bad pair of pants.
Yeah.
And then somehow this has nothing to do with the length
yes.
of your curves.
The thing is that if you want to make sure, so your question is, you want to make sure that you get all the geodesics up to length L. Now there is a combinatorial length, and so there is a discrepancy. And if you have small, close, I mean the cuffs are small, then you're far away from the truth.
Yeah.
And so I'm thinking like examples that near very symmetric ones, and these usually are thick.
So this is about combinatorial length and not geodesic.
Yeah. But in papers, it's always there exists a constant comma such that.
More questions? So we can Peter again. Thank you.